So in this video, I want to talk about this concept of harvesting. Now, I reckon that the majority of people will kind of, an image will spring into their head of, when I say harvesting, of say like a tractor or a combine harvester on a field on sort of a August, September, sort of late summer day. And, they're out there harvesting the crops in the field. That is exactly what harvesting is, okay? It's taking something away. So, for example, you grow crops in a field, you then come in with your harvesting equipment, your combine harvester, your tractors, and you literally take away all those crops which have grown over the years away, and, you use them elsewhere. So you're taking the crops away from the field, okay? And that is all harvesting is. So harvesting is applicable to obviously crops, but it's also applicable to animal populations, for example. So, for example, you have a population and you want to kind of, you might be, for example, have a fishery. A fishery is a good example. So you'll have fish in a fishery, and you can take fish away. You can harvest fish from it, or you can go out fishing in the sea, and you take fish away from it. And this kind of harvesting term is all about kind of how much we can take away or even put into a system, because harvesting is not just applicable to, is not just taking stuff away. It can also be putting stuff back in, for example. Okay, so let's suppose we have, we have our general, our description of how our population changes over time. Okay, so this is just a general description. We've looked at a couple of models now that follow this kind of model. It's just simply the rate of change of our population is given by our population times by some growth rate. Okay, and that growth rate is kind of what we've looked at here. We've looked at the exponential model, where the growth rate is just r. Okay, and then we've looked at the logistic model, where we had to kind of add in an extra term to take into account the fact that the population should, as the population gets to a certain point, it starts to level off. Okay, and that's called the logistic model. But essentially, both models follow this kind of pattern. So we have our population, which grows over time. So we have it multiplied by some growth rate. Okay. Well, now all we do with harvesting is we have an extra term called H, standing for harvesting, which takes into account, our hunting or predation, for example. It could take into account predation. So in other words, this is a simple way. It's a really simple way of introducing immigration and emigration into our system now. Remember, before we only considered a closed system. So in other words, a system where we had a village and we closed it off, or a country, and we sealed all the borders off. Nobody was allowed in or out, and we just considered how the population changed kind of in that closed system. Now we open the borders and we allow people in and out, and that will take, in this term is a very simple way of taking into account that immigration and emigration. Let me show you kind of an example. So let's say, for example, that 1,000 people emigrate. Oops, sorry, that's two M's there. No, there is only one M, sorry. Emigrate from a country of population size N. So that's the population of the country. Okay, and 1,000 people emigrate from that. So therefore, a hunting term in this case, if it's emigration, the hunting term would be 1,000. Okay, because we have our population, and then 1,000 people are removed from that population. And that's taken into account with the harvesting. But now let's suppose that 1,000 people immigrate. Okay, immigrate into a country and a population of size N. So now what we do is we've still got this is describing our population. Okay, but we now have 1,000 people are immigrating. In other words, they're coming in, right? So we're adding to the population. So if we're adding to the population, okay, we're not taking away. At the moment, this term here is saying that, the harvesting term takes things away from a system. So we've only considered harvesting as taking away from a system. That's why there's this minus here. Because, you have a population, say like crops, for example. You come in with your combine harvester and you take crops away. That's why the minus is there. Now what we're saying is that immigration, in other words, people are coming into the country. In other words, we should have more population. So therefore, it should be the opposite. So if the harvesting now is opposite, so we're not taking away, we're actually adding to it. So it's the opposite case. When we have an opposite case, we just use a minus. And now notice that because we've got a minus here, and the harvesting term is a negative as well, a negative is going to make obviously a positive. Okay, so we end up with a positive term, and that kind of gives us what we want. We have more people coming into the population. Let's kind of look at a slightly more kind of a layered example, I suppose. Let's suppose we have 10% of a population deer are killed by hunting each year. Okay, are killed by hunting. Then what's H going to be killed? So 10% of a population N are killed by hunting. So therefore, what we're going to have, a harvesting term is going to be 0.1 times our population, N. It's going to be 0.1 of our population, whatever that population is. So now our hunting term is 0.1. Okay, and obviously you can play around with that. The key is basically at the moment, the whole idea behind the harvesting term is think about it as a crop in a field. You go in, or fishing, for example, you're taking things away from the system. That's what harvesting is. But you know, the way that it works, we can also consider the case when we're adding stuff to the system. So people are coming in. So it takes into account immigration and emigration as well, this harvesting term. Okay, so now it's just a simple way of introducing movement into a system. Okay, let's look at it through an example. Okay, so we've got this example, okay, and this example actually looks at something which is a real-life example, which is what is the maximum number that we can sustainably harvest. So this is a really kind of good example with, say, like fish. You know, cod, for example. The worry is with cod now is at one time there was loads of cod in the sea. Now we've taken out so much cod that the worry is that there's not enough cod left to sustainably keep on fishing at that kind of rate. So this is a really good example. Basically, we have a population. This is kind of a practical example where basically we have a population and we try and work out, well, what's the maximum number that we can harvest without exhausting the population. So in other words, without making the population go extinct. So here we have, let's read through it. A population of shrimp has unlimited resources and its population size grows at a rate of 10% per month. The initial size is 1 million. What is the maximum number of shrimps that may be caught each month without ultimately exhausting the population? So intuitively, okay, I've been underlining things that we've been going through, but intuitively, what would you think what would you think that the maximum number would be? We'll go through the proper solution in just a moment. But what would you think it is? Well, first things first, we've got unlimited resources. So therefore, we know that there's not going to be like a carrying capacity with this population. So we don't have to worry about carrying capacity with the population. Okay. Then we've got that the population size grows at a rate of 10% per month. So whatever the population is, okay, it grows at a rate of 10% per month. Okay, and its initial size of the population is 1 million. So the initial size of the population is 1 million. So we're going to call the population N. So N is the population, as usual. Okay, here we have N is the population, right? N naught is, what's it going to be? It's going to be 1 million, so 1 million. Okay, its rate is 10%. Of the 10% of the population per month. So its rate is equal to 0.1. Okay, it's going to be equal to 0.1, right? And we know it's unlimited resources. So what model is it going to be? What growth model is it going to be? If it's unlimited resources, it means there's no carrying capacity, which means it must be the exponential model. So in other words, we're looking at this. So the rate of change of the population is just given by the growth rate times by the population. Okay, and this will sort it out. Okay, so we have 1 million shrimp, okay, at the start, and it grows at 10% per month. So what is the maximum amount that we can harvest? Well, to me, the maximum amount we can harvest is the amount which is being produced. Okay, so the population is growing at 10% per month. So if we just take all of those population, if we take 10% of the population per month, then that's fine. Yeah, well, I mean, we wouldn't usually take 10% per month because there would be other factors which kind of mean that the population isn't growing at a constant rate. So in actual fact, it would be less. But the maximum number in this case, because it's a simplified model, we're just going to, if we take 10% out of the system per month, then that's fine. Because the next month, there'll just be 10%, but, that 10% will be replaced. The amount that we've taken out will be replaced. So what am I talking about? Well, what's 10% of 1 million? What's 10% of 1 million? Well, it's going to be 100,000. So 100,000. So I'm proposing that we can harvest 100,000. We can harvest 100,000 shrimp per month, because that's the amount being produced each month. Okay, so basically we would keep the population at 1 million if we just harvested 100,000 per month. Because if we harvest that 100,000, then the next month that 100,000 will be put back into the system. Then we can take another 100,000 out. So in other words, it's kind of constantly replenishing it. It will constantly be replenished. If we take 100,000 out, then the next month that 100,000 will be replenished again. We can take 100,000 out again. Next month that 100,000 will be replenished. So in other words, we're not actually exhausting the population. So that's kind of the intuitive thing. But let's have a look at the actual solution, kind of how to solve this problem, to see what it would be. So the question states that there are unlimited resources. So exponential model is appropriate, because like I say, there's no k. So what is the exponential model? Well, it's dn by dt. I've written it down. dn by dt equals rn. But remember, now we've got harvesting term. Now we've got harvesting terms to take into account. So we just take away h. Yeah, because if you remember this thing up here, we've got dn by dt equals this. This is what we're used to at the up to now. But now we've got harvesting terms to take into account of it. So we need to take away h from it. Okay, so here we have take away h. Okay, so r equals 0.1. I've written it down here. R equals 0.1. Yeah, so 0.1 times n, which is our r equals 0.1. n naught equals 100,000. Okay, and so essentially what we're trying to do is we're trying to solve this ODE now. If we can solve this ODE, okay, then we can put in r equals that and n naught equals that, and then hopefully we can find out what h actually is. We're after what h actually is. Okay, so in other words, we've got to try and solve this ODE. Now, there's two methods which we can solve it. We can either solve it by direct solutions to kind of find an exact solution, or we can use phase portraits. And we're going to go through both methods now, hopefully. So here we go. So method one is just finding a direct solution. So direct solution. So what was our ODE? So we had dn by dt equals rn minus h. So sorry, that's h. So basically, the idea is that we're going to try and get everything involving n on one side and everything involving t on the other. So this has got no t's in, so it's absolutely fine. Just divide through by that. So we end up with 1 over rn minus h. Okay, dn by dt. Okay, and then we'll just be left with 1 on this side. Okay, so all I've just done is just divided through by rn minus h. Okay, then just multiply through by dn by dt to get that. Okay, integrate both sides, and then that just becomes a nice integral that we can solve. Okay, so let's have a look at this. So this is obviously t plus some constant. We're going to call that c. We don't know what that is at the moment. Now, this is a little bit more tricky to solve. This integration here on the left is going to be a little more tricky to solve. So I just got that t plus c just by integrating this right-hand side. Okay, but now we're going to look at this left-hand side. So what is the integral of 1 over rn minus h dn? Well, basically, whenever you've got 1 over some function, so this in here is a function, okay, the rn minus h is a function. Whenever you've got 1 over a function, it's normally a good idea to look at logs, okay, because that's more than likely going to be. So what do we have if it's going to be the natural, what is the natural logarithm? Well, if we have the integral of the derivative of the function over the function, okay, then that's going to be equal to the natural logarithm of the function, okay. So in other words, yeah, there we go. So that's going to be equal to the derivative of the function. So have we got that case at the moment? Well, not quite, because what's the derivative of this function with respect to n? Well, the derivative of this rn minus h is going to be r, and we haven't got an r on the top, we've only got a 1. But that's okay, because we can just make this 1 into an r. Can just make this 1 into an r, because, if we turn this 1 into an r, it's going to be r over r, right? So if we just turn this into r over r, we can stick an r here. That's absolutely fine. But we're also going to have to divide. We're also going to have to divide by an r out the front. Okay, because when I multiply through by this, okay, I'm going to, if I multiply through by this 1 over r, what I'll end up with is basically the r's will cancel. Hopefully you can see I'll end up with r over r lots of rn minus h, okay, which is going to be equal to 1 over rn minus h. Okay, the r's will just cancel. So that's absolutely fine to what I've done. It's basically I've made a fudge factor out the front, I call it. Okay, so we end up with r over rn minus h, but that's not what I've got up here, but that's okay because I've put a 1 over r at the front to kind of correct it. It's a correction term. Okay, so now I can just say that the derivative of this thing inside the bracket, the integrand is going to go to the natural logarithm of what's on the bottom, by this thing here. So the natural logarithm of the function, whatever's on the bottom, is going to be rn minus h. Okay, but I've still got a 1 over r multiplying out the front, so I'm going to have to multiply that by 1 over r. Okay, so that's what this integral is saying. Okay, and that's all going to be equal to this thing, so t plus h. Sorry, t plus c. Okay, so this is what I end up with. Okay, so what now is going to be this constant now? I want to find out what this constant is. Right. Well, have I been given any initial conditions? Yes, I have. I've been given the initial condition that the initial population is 1 million. So I'm just going to write 1 million as 1 times 10 to the 6. That's just 1 million. You can write 1 million however you want to write it. I'm just going to write it like that because I'm lazy. Okay, so it's going to be 1 million. So what does this actually mean? Well, when t equals 0, n equals that. That is what n naught is. Okay, so t equals 0. So n of t equals 0 is going to be n0. That's just what my notation means. Okay, so when I put t equals 0 in, my n should be 1 million. So let's do that up here. So we get 1 over r. I know what r is, don't I? I know what r is. It's going to be 0.1. I'll leave it as r for the moment, then maybe I'll change it in a minute, just see how it goes. So ln of r times by, what's this? r n minus h. So n is 1 million. So 1 times 10 to the 6. 1 times 10 to the 6 minus my h here. Okay. And that is, sorry, I'll just write n naught actually. Just write n naught. Okay. Am I making this clear? 1 minute. Yeah, I don't think I'm making this overly clear. So what I'm going to do, okay, this is what I've got written down. So this is my function, okay. This is just what this is up here, okay. But what I'm saying is that when t equals 0, so when I put 0 in for t, okay, I should be able to, I just replace n by n naught, and I know what n naught is, okay. So basically, what I'm saying here is that c is equal to that. That's great, because now I've worked out what a value for c is. I can just substitute this back into my overall thing, so I end up with the 1 over r, natural logarithm of rn minus h, equals t, plus c, which I now know is this. So in other words, we've just found c. Okay, so 1 over r, using my initial conditions, rn naught minus h. Yeah, that's what that is equal to. Okay, so now all I have to do is just rearrange this thing to find what n is. Not n naught, because I know what n naught is, and I was r. Okay, it's just this is. So basically I have to try and isolate this thing. Okay, so the first thing I want to do is multiply through by r. So let's just deal with this. There we go. So just going to deal with this. Multiply through by r. I end up with ln of rn minus h equals rt. This is going to be r over r, so it's going to reduce down to 1. Ln of rn naught plus h. Cool, so this is minus h. Yeah, minus h. So now, rnh, so rn minus h. So if the natural logarithm of rn minus h is equal to that, then rn minus h is going to be equal to e to the power of this. So e to the rt plus natural logarithm of rn naught minus h. Okay, well look what I've got here. Are you happy that this is just the same as this times e to the power of that? Yeah, because if I I've got two things the same base, therefore I can just add the power. So it's going to be so it's going to be e to the RT plus, that. Okay, but, I can just now undo that, if you like, and get back to this. Okay, but look what I've got here. I've got e to the natural logarithm of something. Well, e to the natural logarithm of something, the basically e to the power of natural logarithm just cancel out. So therefore it's just going to be Rn naught minus h. This is Rn naught minus h here. Okay, Rn naught minus h. Yeah, I think I've shown you a proof of that in one of the other videos, which is why I kind of didn't do it there. Okay, so that's fine. Rn naught minus h. Okay, so now I can just isolate n. So I end up with Rn equals e to the RT Rn naught minus h plus h, yeah, and just divide through by r, sorry, to find out what n is. So there we go. Okay, there we go. It's as simple as that. So now I've come up with a formula to find what n is. So what does this mean now? Well, let's set h equals to 0. Let's set h equals 0. So this is 0, okay, and this is now 0. So this is what we end up with. Okay, I can cancel the r's off, so I've just set h equal to 0. So this is, maybe I should have, 1 minute. Yeah, so set h equals 0. I'll write it out below. H equals 0. So n equals e to the RT n naught. Okay, so this is what h equals 0 means. Okay, so if I actually just rearrange this, if I write it around the other way, so n naught e to the RT. Notice that this is just the general, this is the standard general solution for our exponential model, which is what we should expect because it's following an exponential model, so that's absolutely fine. So that's just kind of like a little byproduct. So basically what we want to do, what we need to do is we need to look at this thing up here, and we need to basically ensure that n is greater than 0, because that's what we want to do. We want to basically ensure that the population never drops to 0. Okay, so we always want to make sure, what are the conditions to make sure that n is always going to be greater than 0. So basically we're ensuring that, okay, so basically what we need to do is we need to ensure that this thing, so n equals e to the m naught minus h over r, that's always got to be greater than 0. Okay, greater than 0. So this is, sorry, e to the RT. That's always got to be greater than 0. Well, e to the RT, that's always got to be greater than 0. That's always got to be greater than 0, because e to any power can never be 0 and it can never be negative. So that's always got to be greater than 0. So basically we can just ignore that, because that's not going to affect the greater than 0 part. Okay, so let's just ignore that. Likewise, r, well, we know what r is. We know what r is. It's always going to be, we know what r is. It's 0.1, okay? That's always going to be greater than 0. Okay, but also, yeah, that's always going to be greater than 0, so therefore we can just ignore that as well. We can just ignore that as well. So what we're left with is that Rn naught minus h has got to be greater than 0. It's got to be greater than 0, okay? Sorry, greater than or equal to 0. So in other words, what we end up with is that the maximum amount that it can be can be equal to as well. So it's going to be greater than 0, but it can also be equal to 0 as well. So that's the absolute maximum amount that it can be. We're talking the absolute maximum. Realistically, it's got to be greater than 0, okay? But it can also, that's the maximum, is that it can be equal. The maximum will occur when it's equal to 0. So in other words, if we just make this equal to 0, do a little bit of rearranging, what we're saying is that Rn naught has got to be equal to h. Rn naught has got to be equal to h. So we know what r, and we know what n naught is. It's 0.1 times 1 million. Times 1 million, 1, 2, 3, 1, 2, 3, and that's going to be equal to h. So therefore, what is h going to be? It's going to be 100,000, as we predicted. It's going to be 100,000. So hopefully you just follow that. It's just going to be the algebra. So basically we set n greater than 0 into this thing up here, and, we get that out. And it's going to be h equals 100,000, okay? Now, the second method which we can do it is via the phase portrait. This is the second method of how we can solve our ODE. So remember, our ODE was dn by dt equals Rn minus h. So we try and solve it by the phase portrait. Okay, so what do? Well, n has got to be greater than 0. N has got to be greater than 0 for all of our time values. It's got to be greater than 0 at all times. So therefore, first things first, what we've got to do is we've got to plot our graph of t and dn by dt. So dn by dt is just Rn minus h, right? So this is dn by dt. What's our equilibrium point? Well, our equilibrium point is going to be when dn by dt equals 0. So therefore, Rn is got to be equal to h at that point. Yeah, because I've just set that equal to 0, so therefore Rn has got to be equal to h, which implies that n, so our population at that time, is going to be h on r. So our population at the equilibrium point is going to be h on r. So let's call that the equilibrium point there. It's going to be h on r at the equilibrium point. Let's say it happens there. Okay. And so notice that this is effectively, you know, this is our y, the dn by dt, because it's on this axis. This is our y, and this is equal to mx plus c. Yeah, this is just a standard straight line graph where our gradient is given by r and our harvesting is just given our y-intercept. So we're going to cross the dn by dt axis, or the y-axis, at minus h. So that's where we're going to cross. Okay, so we've got this thing going on. So this is what our graph is going to look like. So we've worked out what the graph is going to look like, and then it's just a case of working out what's going to happen, you know, in each part. So here you can see in this region here, dn by dt is going to be negative, and over here dn by dt is going to be positive. Okay, so if we draw that out on our phase plane, okay, we've got our equilibrium point here, which is h on r, right? To the left of that, we're negative. Dn by dt is negative, so therefore we're moving to the left. Okay, and then to the right of that, dn by dt is positive, so therefore we're moving to the right. So clearly, hopefully, you can see that h over r is actually an unstable equilibrium point. Okay, so in other words, when n equals h on r, that corresponds to an unstable population. Okay, so the population can only survive if n naught has got to be beyond this point. It's got to be beyond this point. So n naught's got to be beyond this point. The reason why we want n naught to lie over in this region over here, we want to lie n naught to lie over. So our initial population needs to lie to the right of this equilibrium point. The reason why is because if it lies to the left, hopefully you can see by the graph that the rate of change is going to be down here. It's going to be negative. Okay, so in other words, you can see from the phase portrait that we're moving to the left. So therefore our population is decreasing. So in other words, eventually it will lead to extinction, which obviously we don't want. Okay, over here though, the population is growing. So the population is growing. So therefore we want our n naught to lie some point over here onto this right hand side. So in other words, what we want is n naught has got to be, sorry, this is when n is greater than. So n naught has got to be at least greater than this point here. So in other words, it's got to lie to the right of this point, because that's when the population is growing, which is what we want. Okay, so in other words, if we just rearrange that, we end up with Rn naught is going to be greater than or equal to h. Okay, so in other words, what's the maximum amount that we can harvest? It's got to be when it's equal to. So in other words, when Rn naught is equal to h, so therefore that implies that R times n naught, that's 0.1 times 1 million, and that's got to be equal to h, which is obviously 100,000. So that's another way of solving it. Okay, so that's just by phase portrait ways. So there's two ways of solving that.